Commander, let's light the sky. Training sharper drone pilots, learning how to fly. Mission ready mindset, safety leading every plan. Skills that build confidence from takeoff through the scan. Tune in at Sky Commander, come join the crew today. Learning smart, fly with purpose, level up your way. We see more, no sooner, that's the edge we're here to spread. See above, go beyond, get ahead.
Okay, let's get started.
I want you to imagine just for a second looking at this flawless, ultra-high-resolution drone map right on your monitor.
Oh yeah, like the really good ones where you can zoom all the way in.
Exactly. The kind where you can zoom in and literally count the individual pebbles on the dirt.
Right.
The edges of the buildings are razor sharp. The colors are, just perfectly balanced. The entire site is stitched together without a single tear or glitch anywhere.
It looks perfect.
Right. It looks like absolute, undeniable reality. But now I want you to imagine that this beautiful, perfect image is completely lying to you.
Yep. It's a terrifying thought.
And because you trusted it, because it looks so good, it is about to cost an engineering firm, I don't know, $50,000 in poured concrete.
I mean, it is the ultimate trap of the digital age, really. A map can look just breathtakingly beautiful, visually flawless, and still be, well, geometrically fictitious.
Geometrically fictitious. That's a great way to put it.
Yeah, and that is the foundational concept we really need to burn into our brains today. The visual polish of a geospatial product has almost zero correlation with its actual dimensional truth.
Zero correlation. And that massive disconnect is exactly what we are unpacking in today's deep dive.
It's going to be a fun one.
It is. We're looking at a huge stack of professional geospatial mapping guidelines today. I'm talking heavy-hitting standards from the U.S. Geological Survey, NOAA's UAS Image Control Guidance.
Natural Resources Canada is in there too.
Right, NRCan, plus several expert operational training manuals. And our mission today is to explore the invisible dividing line between a map that is just, pretty and a map that is actually proven.
Yes, because we really need to figure out why human perception is so easily hijacked by high-resolution pixels.
It really is hijacked.
Oh.
And of course, how professionals actually anchor these digital illusions to the physical planet.
Well, the vulnerability really starts with our own biology, if you think about it.
Wait, biology? How so?
Yeah, I mean, human eyes have evolved to be incredibly sensitive to image quality. We instantly recognize if a photograph is out of focus.
Oh, for sure. You notice that immediately.
Exactly. We notice if the lighting is blown out or if the colors look washed out or artificial. But our visual cortex is just terrible at intuitively noticing coordinate error.
Huh. That makes sense. We don't see coordinates.
Right. Unless there is a glaring, visible conflict I don't know, a road suddenly breaking and shifting 3 feet to the left in the middle of the image, we simply cannot see absolute accuracy.
We see the presentation and we just assume the math is right.
Exactly.
I mean, I look at a 3D model of a construction site generated by a drone, and my brain just processes the clean hill shading, the crisp topography.
The smooth transition between the staging area and the foundation.
Yes. And it just feels authoritative. It feels true because it looks clean.
But we are conflating style with evidence.
Right.
Clean labels, tidy cropping, aggressive color ramps. These are all presentation qualities. They are designed to make the data digestible. But the USGS defines ground truth very specifically.
I'm guessing it has nothing to do with aesthetics.
Nothing at all. They define it as verification that is explicitly isolated from errors introduced by sensors, and more importantly, isolated from human perception and judgment.
Okay, this brings up an analogy from the sources that perfectly illustrates how our perception gets hijacked here.
The picture frame analogy, I love this one.
Yes, the framed portrait. So think of a framed portrait hanging on a wall. Everything inside that frame might be flawless.
The high-resolution print, the perfect right angles of the wooden frame.
Exactly. The proportions of the face in the photograph. Everything inside the frame is geometrically correct relative to everything else inside the frame.
And in surveying terms, that is what the USGS refers to as internal precision or relative accuracy. The relationships between the objects within the data set are consistent.
But if that entire picture frame is hung, say, 20 centimeters to the left of where the interior designer actually wanted it on the wall,
then the frame itself is in the wrong place.
Exactly. That is the critical difference between relative accuracy, which is the flawless picture inside the frame, and absolute accuracy, which is where the frame actually hangs in the physical universe.
And geospatial data can repeat the exact same wrong answer with terrifying consistency.
which is so wild to think about.
You can have a map that is highly precise but systematically biased. You can generate an orthomosaic, which, is just a stitched aerial image that's been geometrically corrected to act like a map.
Right.
And that orthomosaic can cover a massive site without a single missing pixel.
Which really just means the software successfully painted the canvas, right?
Exactly. It doesn't mean the canvas is resting on the correct coordinates.
The software can be overwhelmingly confident without actually being correct.
Yes. Confident, but completely wrong.
That is a terrifying thought for, an engineer or a site manager.
Oh, absolutely.
You're saying the software's internal confidence score has absolutely nothing to do with planetary reality. So, if my eyes are seeing perfect corners and straight lines, but the map is lying, what exactly is the software doing under the hood to build this illusion?
Well, to understand that, we have to look at the mechanical reality of photogrammetry.
Okay, let's unpack that.
When a drone flies over a site, it is taking hundreds, sometimes thousands, of overlapping two-dimensional photographs.
Right.
The software's first job is to solve the scene by finding common features across all those different images. These are called tie points.
But how does it actually do that? Because, the drone is moving, right? The angle is changing. The sunlight might be shifting slightly.
Yeah, it's a dynamic environment.
So how does a computer look at 5 different photos and know, without a doubt, that it's looking at the exact same rock?
It uses feature extraction algorithms. And the key here is the software isn't looking for a rock or a car.
It doesn't know what a car is.
Right. It is looking for areas of high local contrast. So think about the sharp edge where a white painted parking stripe meets dark asphalt.
Oh, okay. That's a huge contrast.
Exactly. It identifies a cluster of pixels around that high contrast edge and translates it into a mathematical descriptor.
A mathematical descriptor.
Then it searches for that exact same mathematical descriptor in all the neighboring photos. If it finds that same pixel relationship in, say, 6 different photos taken from 6 different angles,
Locks it in.
Yep, it locks that in as a tie point.
So it's basically just playing a massive game of...
Not a massive game of memory.
Matching millions of micropatterns across the entire data set.
Millions of them. And by analyzing how the angle and scale of that specific tie point changes across those 6 photos, the software can reverse engineer where the camera must have been in the sky when each photo was taken.
Wow. So it figures out its own camera position just from how the pixels change shape.
Exactly. It uses this triangulation to build a relative 3D point cloud. But here is the trap.
There's always a trap.
Always. That incredibly complex mathematical operation can execute perfectly before you introduce a single real-world geographic coordinate.
It successfully builds the picture frame.
Yes. It built a perfect picture frame. And at this stage, the model is essentially a floating sculpture in a digital void.
A floating sculpture. I love that visual.
It has internal structure, sure. The distance from the parking stripe to the front door of the building is relatively correct.
Because the math worked out internally.
Right. But because it isn't anchored to the planet yet, it possesses a dangerous amount of freedom. It can shift on the X and Y axes. It can rotate clockwise.
Like the whole model just spins.
Just slightly, yeah. It can also suffer from scale drift.
What is scale drift?
That's where the internal distances slowly stretch or compress from one end of the site to the other. So a foot on the west side of the map might not equal a foot on the east side.
Yikes. That's a nightmare for measurements. Or, wait, can it also carry a vertical bias? Like, could the entire 3D model be hovering 4 feet above the actual dirt?
Oh, absolutely. Or buried 3 feet below it.
Wow.
And we can take that a step further into a very specific geometric failure called doming.
Doming. Like a dome on a stadium.
Yeah, exactly. This is a notorious problem in photogrammetry workflows that rely purely on imagery without strong ground control. The software will subtly bow the entire 3D model upward in the middle, like an inverted bowl.
Wait, hold on. Why would it curve the Earth like a bowl? If the drone is flying a flat grid pattern, where does the curve even come from?
It comes from the physical limitations of the camera lens itself.
The lens.
Yeah, no lens is perfectly flat. They all have slight radial distortion, especially out near the edges of the glass.
Oh, right. Like when you look through a magnifying glass and the edges look kind of warped.
Exactly like that. So when the drone flies its lawnmower pattern back and forth across a site, the software is constantly trying to stitch the edge of one photo to the edge of the next.
Okay, I see where this is going.
Right. If the software hasn't perfectly calculated that microscopic lens distortion, the math slowly compounds.
It adds up over hundreds of photos.
Yes. And to make all those slightly distorted edges fit together, the algorithm has to bend the overall geometry. It literally warps the Earth to force the pixels to align.
So it's not just a mapping error, it's a compounding physics error.
Precisely.
The software literally decides that bending reality is the only way to solve the math equation.
Yeah, it prioritizes the math over the reality.
That is wild. But wait, hold on. I need to push back on this whole floating sculpture concept for a second.
Sure, go ahead.
Because I can go to a big box store right now and buy a drone with GPS built into it.
Oh, yeah. Everyone has GPS.
Right. And commercial mapping drones definitely have GPS. So if the drone is tagging every single photograph with a latitude, longitude, and altitude the exact moment the shutter clicks, why is the sculpture floating? Doesn't the drone already know exactly where it is?
That is the misconception of standard GPS, and it catches a lot of modern pilots off guard.
Really? How so?
Standard onboard GPS, which is the exact same technology in your smartphone, by the way, is approximate.
Approximate.
Yes. It is subject to atmospheric interference, satellite geometry, and signal bounce. A standard GPS tag on a drone photo might have an error radius of like 2 to 5 meters.
2 to 5 meters. If I'm using a drone map to determine where a property line sits, a 3-meter shift isn't just an error, it's a lawsuit.
Exactly. Now, a lot of commercial pilots will hear that and immediately counter with, but my drone uses RTK.
Right. Real-time kinematic positioning, or PPK, post-processed kinematic. I see those acronyms all over the drone forums.
Yes. These are advanced GNSS methods that drastically reduce that positioning error.
Let's break down how RTK actually works, because it gets thrown around like a magic bullet.
It really does. So RTK is essentially a two-part system designed to fix the specific errors that standard GPS can't handle. The biggest error in GPS is atmospheric delay.
Okay, what does that mean?
When the signal leaves the satellite, it has to punch through the ionosphere, which is a layer of the atmosphere, and that ionosphere slows the signal down unpredictably.
So the signal doesn't travel at a constant speed.
Right. And if the signal slows down, the drone's calculation of its distance from the satellite is wrong, hence the 3-meter error.
So how does RTK fix the atmosphere? Does it just guess the delay?
No, it uses a base station. You place a highly accurate GNSS receiver, the base station, over a known surveyed point on the ground.
Okay, so a fixed point that doesn't move.
Exactly, because the base station knows exactly where it is, it listens to the satellites, calculates the exact atmospheric delay happening in that specific region at that exact second, and broadcasts a correction signal over a radio link up to the drone, which is the rover, while it's flying.
So the drone applies that correction in real time.
Yes.
Meaning instead of a 3-meter error, the drone knows exactly where the camera is in the sky, down to, what, a couple of centimeters?
Down to a couple of centimeters, exactly. It vastly improves the starting geometry of our floating sculpture.
That sounds pretty foolproof.
It sounds like it, but here is the critical limitation. NOAA's best practices explicitly state that while advanced positioning like RTK improves the data, it does not remove the need to verify the final product.
Okay, I'm trying to wrap my head around why.
Sure.
If the RTK base station tells the drone exactly where it is down to the centimeter, and the camera's pointing straight down at the ground, the math from the camera to the dirt is just a straight line, right? Why do I still need to verify the ground?
Because the camera is not a perfect geometric instrument, and the drone is, at the end of the day, a vibrating piece of plastic being battered by wind.
Vibrating plastic, right.
RTK only tells you where the GNSS antenna on top of the drone is located.
Just the antenna.
Yes. The software then has to calculate the lever arm, which is the exact physical distance from the antenna down to the camera sensor.
Oh, wow.
Then it has to account for the gimbal. If the camera gimbal pitches even a fraction of a degree due to wind resistance, that straight line to the ground is now projected outward at an angle.
Oh, right, because it's so high up.
Exactly. Over a distance of 400 feet in the air, a 1-degree pitch error shifts the pixels on the ground significantly.
And we haven't even factored in the lens distortion we talked about earlier.
Nope. Or changes in focal length because the camera body heated up in the sun and the internal components expanded by like a millimeter.
Good grief.
Yeah.
So there are just a dozen tiny physical variables that can throw the math off.
Exactly. RTK is an elite athlete. It performs at a remarkably high, precise level. But independent ground truth is the drug test.
Oh, that's a brilliant way to put it.
One performs, the other proves. You can have the most expensive RTK drone on the market, but if your camera calibration is flawed or your gimbal is vibrating, your final map can still be completely shifted or distorted.
Which brings us back to the financial and legal liability. Because when an engineering firm hires a mapping pilot, the pilot delivers this beautiful RTK-assisted 3D model.
And they open it up.
Right, the client opens it up, sees the crisp edges of the buildings, and pays the invoice. The disappointment almost never happens on delivery day.
Never. The failure is completely invisible at first.
It happens like 3 weeks later. The engineering firm takes that beautiful drone map and overlays it with an existing CAD design file or a historical physical survey of the property.
And suddenly nothing lines up.
Right. Suddenly, the drone map shows the new access road cutting straight through a protected wetland.
Or it shows the foundation of the new building shifted 5 feet into the neighbor's property line.
That is the exact moment the map stops being a cosmetic deliverable and becomes a massive legal liability.
And this is why we must transition from relying on the sky to anchoring to the earth.
Anchoring to the earth.
Yes. If the drone's telemetry and the software's math cannot be implicitly trusted, we have to force the digital model to obey the physical planet.
Enter the absolute heroes of geospatial science. Ground control points and checkpoints.
The physical tools of truth.
Yes, these are the physical targets on the ground. But before we get into the grueling logistics of actually placing them, we have to establish the core philosophical difference between the two.
This is so important.
Because the sources, especially the USGS, they are militantly strict about this distinction.
It really is the most profound conceptual divide in all of mapping. Let's begin with the ground control point, the GCP.
Okay, what is a GCP physically?
Physically, a GCP is a highly visible target, usually a high-contrast black and white checkered square that is physically placed on the site before the drone flies.
Just laid flat on the dirt.
Yep. And most importantly, the exact center of that square is measured with professional, high-precision surveying equipment.
So you capture the exact latitude, longitude, and elevation of that specific square of vinyl.
Yes. And during the software processing phase, you intervene.
You intervene.
Like manually.
Exactly. You tell the software, I know you think you figured out where this pixel is based on your algorithms, but you were wrong.
I have the real coordinates.
Right. This specific pixel is located at this exact coordinate. You feed the surveyed truth into the algorithm, and the software uses that irrefutable data to pull, stretch, and lock the floating sculpture into physical reality. It translates arbitrary pixels into absolute coordinates. It's the nail that forces the picture frame to hang on the correct stud on the wall.
Exactly. But a checkpoint SCP serves an entirely different master.
Even though it looks the same.
Physically, it looks exactly the same. It is a surveyed target on the ground, but its function in the workflow requires absolute isolation.
Isolation.
Yes. You must hide the checkpoint from the software during the entire processing phase. It is never allowed to influence the adjustment.
You deliberately withhold the data. You don't let the software see it.
You quarantine it. Once the software has completely finished building the model using the aerial imagery and the ground control points, only then do you introduce the checkpoint.
So it's an after-the-fact test.
Yes. You select the location of the checkpoint on the final digital map, and you ask the software, based on all your math, what do you think the coordinates are at this exact spot?
And then?
Then you compare the software's blind guess against the actual surveyed truth of the checkpoint.
The sources use a phenomenal analogy here that instantly demystified this entire process for me.
The flashcard analogy.
Yes, imagine a student studying for a massive final exam. The ground control points are the flashcards.
Right.
The student uses them to learn, to adjust their understanding, to correct their mistakes while they study.
That's the software calibrating itself.
Exactly. But if that same student is allowed to write their own final exam and then grade that exam themselves using the exact same flashcards they studied with,
then the exam is entirely dishonest.
right, it's cheating.
It becomes a circular mathematical argument. If you use a target to stretch the model and then measure that same target to report your accuracy, you aren't asking, how accurate is my map?
You're just asking, how effectively did the software force the map to match the coordinate I commanded it to match?
Precisely. The checkpoint is the external examiner who walks into the room on test day. They didn't help you study. They didn't hand you the flashcards.
They just hand you a blank test to see what the model actually learned about the spaces between the control points.
And the USGS enforces this with rigid mathematical standards. They state explicitly that control points used in calibration shall never be used as checkpoints.
Never. No exceptions.
None. And they require the calculation of RMSE root mean square error.
Okay, let's unpack RMSE because it sounds intimidating when you read it, but it's really just a mechanism for finding the average lie, isn't it?
That is a perfect way to describe it. Finding the average lie.
How does the math actually work, simply?
Well, when you compare the map's coordinate to the checkpoint's true coordinate, there is always going to be an error.
Right. It's never going to be zero.
Never. Maybe the map is off by 2 centimeters on the x-axis, minus 3 centimeters on the y-axis, and say plus 4 centimeters on elevation.
Okay, so we have positive and negative errors.
Right. And to prevent positive errors and negative errors from simply canceling each other out, which would make the map look perfectly accurate, the RMSE formula squares all the error values.
Because squaring a negative number makes it positive.
Exactly. It turns them all into positive numbers. It averages those squared numbers and then takes the square root of that average.
Bringing it back down to a realistic dimension.
Yes. It provides a single, brutally honest number that represents the absolute positional accuracy of the entire data set.
It really is the difference between performative confidence and mathematical proof.
Yes.
If I use a control point to build a model and then show the client a report saying the model matches that point perfectly, I haven't proven the map is accurate. I've only proven the software did what I told it to do.
You're just grading your own homework.
Yeah.
And Natural Resources Canada and RCAN takes this discipline even further in their federal LiDAR guidelines.
Oh, right, the 3X rule. Let's talk about that.
It's intense. They mandate that the survey equipment and methods used to establish the ground checkpoints must be at least 3 times more accurate than the promised accuracy of the final data set.
Wait, 3 times? So if I'm contractually obligated to deliver a drone map that is accurate to within 6 centimeters, the GPS rover I use to measure the checkpoints on the ground has to be accurate to within 2 centimeters.
At a minimum. Think about the operational rigor that demands. You cannot validate a weak product with an equally weak ruler.
That makes total sense. If your ruler's broken, you don't know how long anything is.
Exactly. If your survey equipment is uncalibrated, or if you rush the measurement and accept a sloppy coordinate, your ground truth is flawed.
The whole thing falls apart.
The entire workflow becomes a theater of accuracy. It looks professional on the metadata report, sure, but the foundation is made of sand.
So we have our flashcards to teach the model, the GCPs, and we have our external examiners to test the model, the checkpoints.
Right.
But simply possessing these tools isn't enough, is it? The physical distribution of these targets across the Earth is just as critical as their mathematical precision.
Oh, distribution is everything.
Because if I'm mapping, say, a massive 300-acre solar farm installation, I can't just toss 5 targets out the window of my truck in the parking lot and assume the whole site is locked down.
And yet, that is perhaps the most common operational failure in drone mapping.
Really? People just group them up.
All the time. People fall victim to the myth of more targets. They assume that sheer volume solves the geometry problem. But raw point count matters significantly less than point distribution.
But 10 bad points are worse than 6 good points.
Oh, absolutely.
Yeah.
10 clustered, poorly placed points are mathematically inferior to 6 strategically distributed points.
Which brings us to the most relatable yet devastating trap mentioned in the operational manuals. The truck cluster.
The truck cluster. It is so real.
Let's paint the picture for the listener. Imagine I'm a pilot, and I pull up to a massive site in the middle of July. It's 90 degrees outside.
The sun is beating down on you.
Yes. My survey rover weighs 15 pounds. The terrain is covered in thick brush and ravines. I mean, human nature just screams at me to place 80% of my targets within a 5-minute walk of the tailgate.
It is entirely human. The truck cluster is a triumph of human convenience over geometric stability.
And what happens when you process that data?
Well, the 3D model behaves impeccably near the parking lot. The software has an abundance of ground truth to anchor that specific quadrant.
Because that's where all the targets are.
Right. But the rest of the model, the other 280 acres stretching out into the distance, is entirely unconstrained.
The tent analogy works perfectly here.
Yes, explain the tent.
So if you only stake down the front door of a massive circus tent, the back half of the canvas is just flapping in the wind.
It has total freedom.
Right. It can wander, it can twist on the z-axis, it can drift wildly in elevation at the far end of the site.
Exactly. And to properly stake down the tent The USGS provides uncompromising guidance. They require checkpoints to be well distributed across the entire project area.
Do they give a specific geometry?
Yeah, for a standard rectangular flight plan, they suggest spacing points across the diagonal extent of the site, ensuring that a minimum of 20% of your total points are located in every single quadrant.
Every quadrant. So you can't ignore the back corner.
You cannot. You must explicitly control the outer perimeter to prevent the doming and tilting we discussed earlier, and you must place points throughout the interior to anchor the center.
You have to respect the geometry of the risk.
And NOAA actually conducted a fascinating study on this exact dynamic in coastal wetland environments.
Oh, yeah. The wetland study. They tested different control layouts against each other, right?
They did, and the data proved that evenly spaced, regular grid distributions reduced overall model error significantly better than clustered layouts.
Did they find a magic number? Like a point where adding more targets stops helping?
They did find a threshold of diminishing returns, yes. In their specific coastal setting, once they achieved a distribution density of about 1 GCP per hectare.
Per hectare, okay.
Right. Once they hit that, adding more control points did not yield any massive improvements in accuracy, provided that the initial spacing was disciplined.
So geometry outperformed raw density every time.
Every single time.
But I want to complicate this because a real-world site is never just a perfectly flat grid of identical dirt.
Very true.
Let's say I'm mapping a massive municipal park. The eastern half is a freshly paved, flat asphalt parking lot.
Nice and easy.
Yeah. But the western half is a sprawling field of dense, knee-high grass. Does a black and white checkered target look the same to the photogrammetry software on the pavement as it does sitting in the grass?
That is a critical variable, and frankly, it is a nightmare for vertical accuracy.
Really? Why is it a nightmare?
Because different surface conditions perform completely differently during the tie point extraction phase.
Is it because the grass is physically moving in the wind?
That is the primary mechanism of failure, yes. Imagine the drone takes photo number 1, and a blade of grass is leaning to the left. A split second later, it takes photo number 2, but a gust of wind has pushed that blade of grass to the right. The software's feature extraction algorithm tries to match the high contrast tip of that grass blade across both photos, but the pixels have physically moved in relation to the Earth.
So the algorithm is just chasing moving targets.
Exactly. This creates massive vertical noise in the point cloud. Furthermore, in dense vegetation, the camera simply cannot see the actual dirt.
Because the grass is blocking it.
Right. So the software ends up averaging the noisy tie points at the top of the grass canopy, creating a false digital floor that hovers like a foot or two above the true ground level.
While the paved parking lot, on the other hand, is completely static.
Exactly. The painted lines don't move in the wind. The asphalt is hard, stable, and incredibly easy for the software to model.
So if a pilot is physically exhausted, going back to the truck cluster idea, they will naturally place all their checkpoints on the easy paved surfaces, avoiding the miserable hike through the tall grass.
Oh, absolutely. They stay on the pavement.
But doing so means they're giving the software an open book test on the easiest possible subject.
That is exactly what they are doing. They are only proving the map's accuracy in the places where the map was already guaranteed to be accurate.
And the USGS standards anticipate this exact bias, don't they?
They do. The guidelines mandate that checkpoints must be distributed among different land cover types in approximate proportion to their presence in the overall project area.
That is so smart.
It is. If half of your site is vegetated, a proportional number of your independent checkpoints must be placed in the vegetation.
You have to test the software's ability to model that specific, difficult terrain.
Exactly. If you fail to do this, your final RMSE accuracy report is a mathematical fiction.
Okay, let's step back and look at the reality of implementing all this. Because doing this correctly, surveying highly accurate GCPs, fighting human nature to distribute them across all 4 quadrants, dragging equipment through dense vegetation, mathematically quarantining independent checkpoints, it is incredibly expensive.
Oh, it is extremely resource intensive.
It requires specialized GNSS hardware, software subscriptions, hours of grueling physical labor in the field.
Yeah, you're out there sweating.
So the question is, does a professional pilot actually need to deploy this massive survey-grade network every single time the drone leaves the ground?
Absolutely not. And this is the most important operational pivot a professional makes.
Okay.
Accuracy is not a slider that you simply crank to maximum for every flight. Accuracy is a business decision dictated entirely by consequence.
Dictated by consequence.
Yes. A true professional matches the mathematical rigor to the financial or legal risk of the project.
Let's weave this into a narrative, because the sources outline a consequence ladder that perfectly demonstrates how this risk scales.
It's a great framework.
Let's follow a single drone pilot working with an expanding development company. The pilot gets their first call. The developer wants a drone map of a newly purchased 50-acre lot.
Okay, the first job.
They just want to put the map on a brochure to show investors the general layout, where the trees are, where the access road enters the property.
Right, so we are at the bottom of the ladder. Visual context.
Visual context.
The risk here is virtually zero. Nobody is using this map to measure property setbacks. Nobody's using it to order building materials.
It's just a pretty picture for a PDF.
Exactly. In this scenario, deploying a robust ground control network is a massive waste of the client's money and the pilot's time. Standard onboard GPS positioning is entirely sufficient to stitch the map together for visual context.
But the pilot has to ruthlessly define that in the contract, right?
Yeah.
They have to stamp the map saying, this is not for measurement.
Oh, they must actively defend against scope creep. Because the danger arises when the client takes that unanchored visual map and suddenly tries to use it for engineering.
Which naturally happens as the project evolves.
Always.
Like 3 months later, the client calls the pilot back, the brush has been cleared. The site manager says, hey, fly the site again. We need the map to figure out the logistics for the month. Where should we park the excavators? How much space do we have for the staging area?
Okay, now we have moved up to operational reference.
Operational reference. The stakes are a bit higher.
The map is being used for rough logistical planning. You need the geometry to hold together reasonably well so the site manager can trust the general distances, but you aren't defending these measurements in a courtroom.
So what's the control plan here?
A modest control plan is required here. You might place a few strategically distributed GCPs to buy mathematical trust and stabilize the floating sculpture, but you don't need a grueling survey-grade validation network.
Okay, but then the heavy machinery arrives. They start digging the foundations and piling up thousands of tons of expensive gravel and topsoil.
The dirt starts moving.
Right, the client calls the pilot. Fly the site every Friday. I need you to calculate the exact volume of dirt in those stockpiles so I can pay the earthwork contractors.
The gloves come off. We are now at repeatable measurement.
Repeatable measurement.
The fundamental nature of the mapping has changed because you are now executing a time series comparison. You are comparing the map from Friday the 12th to the map from Friday the 19th.
Which means the invisible digital coordinate frame has to be absolutely locked down.
It must be bolted to the planet. If the pilot relies purely on the drone's GPS, the map from the 12th might float a meter to the east. The map from the 19th might float a meter to the west.
And carry a vertical bias. Like hovering 6 inches too high.
Exactly. And if the floor of the 3D model shifts up by 6 inches across a 10-acre site, the software will calculate that shift as phantom dirt.
Phantom dirt.
Yes. It will look like the contractor brought in thousands of cubic yards of material that didn't actually exist, or it will look like an entire retaining wall physically moved 2 feet over the weekend.
And the client is paying for that phantom dirt. That is real money.
Real money. Repeatable measurement severely punishes inconsistency. Stockpile calculations are incredibly vulnerable to vertical bias. This level of consequence requires deliberate ground control and independent checkpoints every single flight to prove that the reference frame hasn't drifted.
Which brings us to the final boss, the top of the ladder.
High consequence integration.
Right, the buildings are going up. The engineer needs the drone map to finalize the pouring of the concrete footings along the edge of the property line to ensure they don't violate municipal setback laws.
This is the danger zone. The drone map is no longer living in isolation. It is being integrated directly into engineering design files, legal boundary surveys, and formal municipal reporting chains.
The sources specifically mentioned roof inspections and property lines as notorious traps for high-consequence mapping. Why roofs?
Roofs are the perfect photogrammetry trap.
How so?
They have sharp, high-contrast edges. The feature extraction algorithms love them. The software can stitch a roof map incredibly fast, producing a visually stunning, razor-sharp orthomosaic.
Right.
But that sharp visual edge creates immense emotional trust.
Ah, I see. So the solar installer looks at the crisp edge of the roof line and thinks, this map is flawless. I can use this to measure the exact square footage for the solar array down to the millimeter.
Yes. But if that beautifully stitched roof was built without rigorous ground truth, the entire structure might be shifted 2 feet into the neighbor's airspace in the digital model.
Oh, man.
If the client uses that shifted data to justify a structural decision, it leads to a catastrophic error. High-consequence integration demands defensible, documented proof.
And the USGS has rules for this, right?
Yes, the USGS mandates that for this level of work, you must provide survey reports documenting the exact coordinates of the GCPs used for calibration and the independent RMSE results of the quarantine checkpoints. You are no longer just delivering a map, you are building an evidence chain.
An evidence chain. That completely shifts the entire paradigm of the job.
It really does.
Like a drone pilot asks, will this data successfully process in the software? But a geospatial professional asks, will this data survive cross-examination?
That is the exact mindset. They start by defining the consequence, and they work backward to design the geometry.
They think about the final moment of use before the drone ever leaves the truck. How will I prove this map is telling the truth?
Exactly.
So if the financial stakes are this massive, and a shifted coordinate can ruin an engineering project, it begs a very obvious question.
Okay, what is it?
Why doesn't the government just mandate the math? If I'm flying a commercial drone in the United States or Canada, why isn't there a federal aviation rule that says thou shalt use 6 well-distributed GCPs and 3 independent checkpoints for any measurement task?
It is a completely logical assumption, but the reality exposes a massive, often misunderstood gap between aviation law and geospatial science.
Okay, what's the gap?
The definitive answer is the government does not mandate your mapping math.
Because flight legality and mapping defensibility are 2 completely separate universes.
Entirely separate. Let's examine the regulatory frameworks. In the United States, commercial drone operations are governed by the FAA under Part 107.
Right.
In Canada, operations fall under Transport Canada's Canadian aviation regulations, specifically Part 9X. Both of these massive legal frameworks are overwhelmingly obsessed with one singular concept.
Let me guess. Safety.
Safety. They care about the airspace. They care that you check the weather, that you aren't flying over innocent bystanders, and that you are maintaining visual line of sight with the aircraft.
Right. Under FAA Part 107.49, the pilot is legally required to assess the operating environment, identify ground hazards, and brief the crew.
Yes. And Canada's CR 901.27 mandates a thorough site survey to confirm the operational volume is safe.
And didn't Canada just do a bunch of updates too?
Yes, recent updates for late 2025 introduced structured operational categories like Level 1 Complex and specialized RPAS operator certificates designed to heavily regulate beyond visual line of sight, or BVLOS, flights.
But if you scour those hundreds of pages of federal aviation law, you won't find a single paragraph dictating RMSE thresholds or land cover distribution for checkpoints.
Not a single word. Because the Federal Aviation Administration and Transport Canada only care that your 60-mile-per-hour flying robot does not collide with a manned Cessna helicopter or plummet into a crowded intersection.
Right. They do not care if your digital point cloud calculates a stockpile volume that is off by 14%.
They do not care at all, and that creates a wild operational paradox.
The paradox of the legal but useless map.
Exactly. You can execute a mission that is 100% legal. You have your Part 107 certificate, you secured LANC airspace authorization, you conducted your safety briefings, and you flew flawlessly.
But because you didn't understand photogrammetry, you can produce a drone map that is completely legally useless as a geospatial product.
And the inverse is equally true, and perhaps more common among rogue operators.
Oh, the illegal but perfect map.
Right. You can meticulously place 20 survey-grade GCPs, reserve 5 independent checkpoints, and produce a mathematically flawless survey-grade geospatial product.
But if you flew your drone into Class B controlled airspace without authorization to capture the photos,
you have blatantly violated federal law.
You cannot use the rigorous rules of geospatial measurement to excuse a failure in aviation safety.
No, you cannot.
And you cannot use a pilot's license to excuse a failure in geometry. You really have to master 2 entirely different disciplines independently.
And this is how a true professional handles the inevitable client question. When a client asks, do you legally need to place all these expensive ground targets? The professional response is, not because the FAA demands it. I need them because your engineering specifications demand positional proof.
That requires such a disciplined mindset in the field. To help lock that mindset in, the operational training manuals provide a fantastic mnemonic device that really synthesizes everything we've covered today.
Oh, the ACT acronym. It is the perfect field checklist.
ACT, anchor it, check it, tell the truth.
Yes, anchor it. If you do not anchor it with ground control points, your digital sculpture will drift from reality.
Check it.
If you do not check it with independent quarantine targets, your model will confidently lie to you.
Tell the truth.
And if you do not tell the truth about your workflow, if you obscure your RMSE report or misrepresent the visual map as a measurement tool, your professional reputation will eventually collapse.
Anchor it, check it, tell the truth. It so elegantly encapsulates the dense standards of the USGS, NOAA, and NRCan into a field-ready philosophy.
It really represents the evolution from simply being a drone operator who takes pictures to becoming a true geospatial professional who captures reality.
Because control tells the algorithm where the Earth actually is.
Right.
And checkpoints tell the human whether the algorithm actually listened.
Visual polish is just presentation. Independent mathematical validation is proof.
We have dissected an incredible amount of technical theory today. I mean, we've mapped the vulnerability of human perception, deconstructed the floating sculpture of photogrammetry,
Explored the physics of RTK and lens distortion.
navigated the truck cluster trap, and climbed the consequence ladder of risk.
Yeah.
But as we close out this deep dive, I want to leave you, the listener, with a final provocative thought about where this entire industry is headed.
The technological landscape is accelerating violently right now.
It is. Consider the trajectory of the hardware and the software. Drones are becoming incredibly cheap, intensely automated, and packed with sensors.
Yes.
Simultaneously, cloud-based AI processing is becoming so sophisticated that within a few years, anyone, literally anyone with a credit card, will be able to launch a drone and generate a beautiful, razor-sharp 3D model with the push of a single button.
The software will autocorrect the lighting, sharpen the edges, and stitch the orthomosaic flawlessly.
The sheer mechanical ability to generate the visual product is rapidly becoming commoditized.
It is.
So if the machine can manufacture the pretty picture automatically and essentially for free, where does that leave the human professional?
That is the big question.
It means the future value of a human pilot won't be rooted in their technical ability to make the map. The software will do that.
Right.
The human's value will reside entirely in their legal and geometric ability to certify the map.
The drone operator of the near future is no longer a flying photographer. They are transforming into a specialized auditor of reality.
An auditor of reality. What happens to the entire mapping industry when the pretty picture is free and only the proof costs money? It all circles back to the jarring premise we started with today.
It really does.
The next time you are staring at a flawless, ultra-high-resolution drone map on your screen, do not let your eyes be seduced by the sharpness of the pixels. Ask yourself the only question that matters. Is this map telling me the truth?
That's a wrap on today's mission, Commander. See above, go beyond, get ahead. For more training, tools, and intel, head to skycommander.ca. If you learned something new, share it, subscribe, and leave us a 5-star debrief.